Hi, and welcome back to this tutorial on building a convolutional neural network in Java from scratch. We are going to be taking a look at our convolution layer backpropagation. This is the nastiest part of this whole process. It involves some calculus. Links for other resources will be somewhere, easy for you to find, and obviously code available as well for you to kind of work through. Here we've got our overview of what the convolution layer does. We have an input, we apply a filter to it with a step size, and we get an output. Now the forward pass process that we covered in the last video, we're kind of sliding this filter over across the input, and each time we slide it, we get an output by multiplying each filter value by the input value underneath that filter. So you can see we get these really long expressions. So when we're looking at the backpropagation, what we're trying to do is work out how each of these filter values here contributed to our error. So we get some error back, which tells us how wrong our output was, and we want to work out how much each of these filters contributed to that loss, or that difference between the desired output and the actual output. So yeah, from our previous layer we get this loss, change in loss relative to the change in output, and we would like to work out how much each value in our filter contributed to the total loss. And that way we can update our filter by adding the current filter to this filter loss, or I guess subtracting it to get it closer to what would have been a perfect output. And that creates this updated filter. So we want to find this filter loss, and how are we going to do that? Well, we are going to use the chain rule. So refresh your calculus before trying to tackle this. We're trying to find dl by df, so that is the loss relative to the change in the filter value. In this specific instance we're looking for filter value 1,1, so that's this value here, but we would do this process for each of these filter values. And what is that equal to? Well, that is equal to the loss per output, so this guy, dldo, so that's what we get from the previous layer when we're doing some backpropagation, multiplied by do by df, so how much the output changed relative to the filter. And what does that equal? Well, we want to see what our loss per output at 1,1 was relative to how our output at 1,1 was affected by filter 1,1, plus the output at 1,2 multiplied by the change in output 1,2 relative to filter 1,1. So remember, we're just looking at filter 1,1, and that will give us these terms here, this do by df. We just need to work out this equation, basically. We just need to work out these do's by df's. From that slide before, here, we get these big long equations which show how each output is calculated, and here they are again. So what we want to do here is differentiate our output 1,1 relative to filter 1,1. do11 by df11, well, all of these are constants, none of these contain any f11 terms, except for this first one. This contains the f11 term, and x11, f11, take the derivative of that, and we're just left with the x11. Follow this process for each of our outputs, and we get all of our derivatives of our output values relative to our filter at 1,1. So our output loss that we got from the previous layer multiplied out by all of these values here, and these are all summed. Yeah, so we're going from this equation to here, substituting x11 for do df11. That's how the math works. How does this look? Let's kind of visualize this process. Coming in here, here's the equation we just had on the last slide, and looking at kind of each of these different values. We were just looking at filter 1,1, and you can see we're multiplying our x11 by our dldo11, and then our x13 by dldo12, so that's in here, and our x31 by dldo21 in here, and so on. And you can see that these points that we're multiplying and summing with our loss output, they're spaced out by what was our initial step size. So remember, what we're doing here is trying to figure out how much each of these filter values contributed to the loss. And this makes sense, because if you imagine we're just looking in the top corner of our filter, so filter 1,1 here. every time we slide over to check the next spot, to do that convolution with each next place, we are sliding over by the step size. So this value, our filter, got multiplied by x11, and then it got multiplied by x13, and then it got multiplied by x31. And all of those ended up in different parts of the output, but they did contribute to that loss. So this kind of makes sense, and this is kind of what we would expect. So we're kind of sliding this along, and what you see is that this kind of looks like a convolution, except our output loss matrix has been spaced out by our step size. You can imagine this would make sense if we kind of spread this out, stretched it out to a 3x3, and put space in the middle, and then just convolved along as we go. So we're taking our DLDO and we're modifying it so it's kind of stretched out by our step size, and then we can just do a convolution with our last input, whatever our last input was. And that will give us our filter loss. So that will result in a matrix that contains all of these loss per filter derivatives. So then from there we can update our filters and we're golden. So that is the process for updating our filters in mathematical terms. Let's take a look at the code. Alright, so back in here, first things first is we want to create a method that spaces out our matrix by our step size so that we can do that convolution to get our loss per filter value. So let's create a function called space array. And what we're going to do here obviously is nothing if our step size is equal to 1, so we don't want to spread it out, it will just be as it was, so we'll just do a little check here. We are going to work out what the size of our output's going to be. So you'll notice this is the same, a very similar formula to our convolution size, but not quite the same. I implore you to work out how I get these values. Cool, so now we're going to create our output matrix with those dimensions. Alright, so now we're going to move along our input by rows and columns. And then we're going to set our output value. Cool, so what's happening here is we are just stretching out each index of our input by the step size, so just multiplying that index by our step size. And then we're going to return our output. Awesome, so now we have the space array function. Let's get our filter loss. Alright, so coming down to our backpropagation function, something we want to think about is that we might have multiple input images into our convolution layer, which means that each filter might get applied more than once. So it might contribute to loss from each of our input images when it was convolved with that input image. So what we actually want to do is get our filter loss for each convolution with our input and add that up for each filter. So we expect a filter loss for each input, and we want to add that all together to get our total filter loss so we can update the filter, and hopefully it will be better for all of the inputs on average. So first of all, I'm going to initialize a filters matrix. So let's just create a filters delta matrix list. And let's create a new matrix for each of these filter updates. and hopefully you'll see why I do this in a second. We need to save our last input. As you could see in that previous PDF, we did a convolution with our previous input. So with this forward pass, I'd like to set our previous input, which means that we need some kind of variable up here. Cool, so now let's set this in our convolution forward pass. Sweet. So now back in our backpropagation function, we can work out how much each filter contributed to its delta, so its loss, for each particular input. So let's start by creating a for loop for each input. So now for each input, we're going to go through each filter and see how much that contributed to our output loss. So we're going to get our current filter. So now we are going to find the corresponding error that we got for this input and this particular filter that we're looking at. So this is our current DLDO value. Sweet, and then now we're going to space out that error array. And then finally we're going to do a convolution between our last input and this spaced out error array. And for this example, remember we're using a step size of 1, and that is just for our backpropagation because we've already accounted for the step size by spacing out our error. So now we actually want to update our filters, and what we need for this to happen is a learning rate. So we want to know how much we should multiply these values here before we add or subtract them to our current filters. So if we scroll up here to our convolution layer, let's add a little learning rate. And we'll just set that in our constructor. So now back in our backpropagation function, what we would like to do is multiply this error, matrix error, by our learning rate and then add that to our new filters. Now currently there isn't a way to add or multiply these double arrays in the way that we are wanting to. So let's go ahead and create a utility class that will have some helpful features for us to do that. So in data I'm going to come in here and create a new class, and I'm going to call this matrix utility. Alright, so what we want is a function in this matrix utility that can add two matrices. And this is going to do what you would expect. We're just going to go through each of these rows and columns and add them together, and that will be our output. Sweet, and I think I'm going to just go ahead and do the same thing for a one-dimensional vector. Sweet, so that was easy. And now we're going to go ahead and create a function for multiplying this matrix by a scalar. Cool, and then we're going to do the same thing again for our vector. Alright, so now let's use those multiply and add functions to turn this filter loss into some usable delta and update our filter. Cool, so we're multiplying our learning rate by -1, and that is because if we contributed +10 to the error, then we might want our filter to shrink by -10, if that makes sense. So reversing that sign. And then we're going to take this delta and just add it to our filter's delta up here. So add it to whatever was currently in that array, and the reason we do this again is because this filter contributed errors in each of our inputs. We're summing up all of our errors for each filter for each input. And now after we've done all this, let's go ahead and update our filters for real. So here our modified new filter is just the sum of our current filter added to our change, I guess, our delta for that filter. Sweet, so now our layer is learning. It is updating its filters. But obviously there's still one more thing we need to do for backpropagation, and that is send our errors back to the layer behind us. So let's go back to the PDF and take a look at how that works. So how do we get the errors for the previous layer, i.e. backpropagate back through the neural network? Well, first of all, something to note is that the output of the previous layer becomes the input for the next layer. So therefore our loss for the previous layer, our DLDO, is actually just our DLDX, i.e. what was our loss relative to our input. So again, we're going to employ the chain rule. So we're going to find DLDX by multiplying DLDO by DODX, so how much our output changed based on x. And for our example here, we're looking at x11. This is multiplying through DLDO for each of our outputs with how much that x contributed to that output. So DLDO11 by DO11 DX11, DLDO12 by DO12 DX11, and so on, finding that x11 here. So how does that look? Remembering way back from that slide, this is how we calculated that output 11, so let's go all the way back to here. So that's this equation here, taken by multiplying these values with our filter. So coming back here, this is really similar to the last step. You'll hopefully recognize if we're trying to differentiate O11 with respect to X11, so how much did this output change with X11, we find that when we differentiate, the only term here with X11 is F11. And actually, none of these other values none of these other outputs contained any reference to x11. x11 was only used in this particular output. And we do this for each output, and we do this for each x input. And then for this particular example, our loss for x11 is just our loss per output 11 multiplied by f11, which comes from here. Now if we do this, for example, a different x, so let's take x33, we see that, this actually does appear in several of these outputs. So differentiating this output with respect to x, we get different filter values. And that contributes here with our loss per x. We take our loss per output multiplied by f33, so on, so on, so on. Feel free to pause, this is a lot to wrap your head around, but hopefully you're kind of following. Again, this is how the maths work out, but let's take a little look at how this is visualized. So first of all, I'm going to rotate our loss, our output loss. You'll see why. I'm kind of mirroring it on both axes, and then I'm going to colorize each of these cells so that we can track them. This is what our desired output is. So we want an output from this calculation that is our loss for each input value. So this loss per each input value is going to be the same size as our input for our convolution layer. Calculating this value up here, we do that by multiplying this f11 value by dld011. To find this dldx12 value, we multiply by f12, and we multiply f12 and dld011. And you can see we're kind of getting the sliding square of colour coming across as we move which loss input we are trying to calculate at that time. Giving you a bit more of a cohesive view, this is our next layer down, and our next layer down again. So if you can kind of see what's happening, it's as if we're sliding this output loss, and it's been spread out along our filter. And if you have done a bit of research prior to this video series, and you might recognize this as a full convolution. So in this full convolution, we're calculating our loss per input by sliding our spread out loss matrix across our filter and doing what is called a full convolution. Now, how is this spaced out? Well, this is actually spaced out by our step size again, so this is kind of familiar to what we saw earlier in the video. Yeah, basically this looks like a full convolution, except our output loss matrix is spaced out by our step size, and it's also flipped on the x and y axis. Our dldx, so that's what we want to pass out to the previous layer, remember? It's just a full convolution between our filter and our spread out and flipped loss. And we will take a look at that code now. So, back in here, we want to create a function that flips our matrix horizontally and flips our matrix vertically. So let's go ahead and create those functions. So here we're just saying our output, basically working backwards, is equal to our input. So just reversing horizontally, and we're going to do the same thing for vertical. Sweet, so now we've got something for flipping our array vertical and horizontal. Now what we need is a function for a full convolution. And now this is quite similar to a convolution, as I said, but we're sliding the whole filter over. So I'm going to come up and copy and paste our convolve function. And we're going to rename this full convolve. Now in this instance we're only going to be using a step size of 1, so I'm going to get rid of that. Which means that we can get rid of these here. And now instead of starting I at 0, what we're actually going to do is start I at negative the filter versus 1. So if the beginning of our input image is 0, then the filter might actually start at a negative index behind it. Hopefully that makes sense. If you understand in the PDF here, this can start at a negative value. If this indice is 0, 0, then this out here is -2, -2. We're going right up to the edge of our input with our filter. Now, of course, we don't want to be indexing inper. That's a spelling mistake. Distracted. Change that. What was I saying? Oh yeah, okay. So obviously we don't want to be multiplying. If we look here, we don't want to be calculating these values here because we're not multiplying them by anything. We only want the indices that are actually valid, so we're only calculating for indices that are greater than 0. And on this end, we're only calculating for indices that are less than or equal to the last index of this input matrix here. So before we add the sum, we're just going to do a check to check that our row index and column indexes are valid. We will add our value in there. Otherwise we won't do anything, so we're not going to index any funky values. Alright, just a heads up, I made a mistake with this convolution layer. What we actually need to do here is add the filter length, not subtract it. So I just copy and pasted from the convolve method, but of course here our filter is sometimes bigger than our input, and that works for a full convolution because we slide the filter all the way over the input. So just a little side note there. That's our full convolution done. Alright, so back up in our propagation function, let's create a list to keep track of the errors for the previous layer. And then for each input, because remember we're calculating the error for each input, we are going to create a new matrix to keep track of that. Sweet, and then for each filter, remembering that our process here is doing this full convolve with each filter in each of the previous losses, we want to do that full convolution. So we're going to flip our error. And then we're going to do a full convolution of this flipped and spaced out error with our filter. So we're going to take this error, because remember that each input had the same filters applied to it as every other input. We are going to add this error onto our existing error for this particular input. So adding that to our existing running total. And then after we've done that for all our filters, let's add to this array here our sum total across all the filters for this input. Sweet, so now we've got our error for all our layers. Now we just need to finally propagate to the previous layer. Sweet, and that's how backpropagation's sussed. Now just need to fill in this little guy, which will just convert as per usual from our vector to our matrix. Awesome, and that's our backpropagation sorted. And with that, I believe we have our entire convolution layer completely done. So now in the next episode we finally get to put all of these moving parts together into a network.